Hey guys, Atam this side और आज हम solve करने वाले हैं आज का LeetCode question which is problem number 1463 cherry pickup 2. It is very easy problem, just the tag is hard, right? So let's first read the problem. In this problem we are given a row and column matrix, right? Grid. The name of the matrix is grid, representing a field of cherries, right? So you are basically given a matrix in which each cell represent some number of cherries, right? Some number of cherries represent the number of cherries, that is grid of ij represents the number of cherries. That's what it means. That you can collect from ij cell, right? That you can collect from ij cell. You have two robots that can collect your cherries, right? You have two robots, robot 1 and robot 2, located at the top left corner and top right corner, right? So here and here, right? Top left corner would be this and top right corner would be this, and the coordinates are also given. What you have to do is you have to return the maximum number of cherries collection using both robots by following the rules, right? So what these both robots which are placed here will do, they'll move some in some manner and they'll keep on collecting the cherries, right? And as they are already present on the left corner and the rightmost top corner of the grid, so you have to consider these cherries, right? So you have to consider these cherries, right? So let's first read the movements of the robots, right? So the robot can move like I plus 1 j minus 1 I plus 1 j I plus 1 j plus 1. So what it means, let's understand. Let's say your robot is in this cell, right? So your robot can move I plus 1 j minus 1 would be this I plus 1 would be row increased. If this is ij I comma j, right, this would be I plus 1, which means row is increased, and this would be j minus 1, which means column is decreased, right? So this would be I plus 1 and j minus 1. Next would be see this I plus 1 j, which means only the row is increasing, which means I plus 1 and j, right? This is the second movement. Third movement would be I plus 1 and j plus 1, right? So I plus 1, which means row is increasing, and j plus 1, which is column is also increasing. Then I plus 1 and j plus 1, right? This is the third movement. So what are the three movements you have encountered so far? Let's quickly summarize it. So these let's suppose ij, your robot 1 or any robot was here. A robot can move in this direction, cross diagonal, left diagonal, straightward, downwards, and right diagonal, right? Your robot cannot move in left direction, right direction, or any of the upward direction. Any of the upward direction means neither left upper corner, neither right upper corner, or nor upwards, right? So these all five movements are prohibited. Only three movements are allowed, right? So this is the movements of the robots in which the robots can move, right? So what are the other points? Whenever any robot passes through a cell, it picks up all the series, right? Let's say this was your grid, and this is your robot 1, this is your robot 2. Robot 1 is present here, robot 2 is present here. It says that when the robot passes through a cell, when this robot will pass through this cell, it will pick up all the cherries, right? It will pick up all the cherries of mentioned in that cell. What cannot happen is it won't pick up like 2 or 1. It has to pick up all the cherries that are present in that cell, right? So this is the second point. Third point is when both robots stay in the same cell, only one takes up the cherries. For example, this movement, let's say both the robots came here. It means that third point says that if when both the robots are on the same cell, only one of the robots can take the cherry. For example, if both the robots are here, then only you will count 5 cherries only once, which means only one of the robot will be able to pick up these cherries, right? And fourth point would be both robots cannot move outside grid. Obviously robots cannot go outside grid in any manner, right? In any manner. Both robots should reach bottom. The last point is important. Both robots should reach bottom row in the grid, right? Bottom row in the grid is what? This row. It means that both the robots have to make the movement somehow collecting the cherries all the way, and finally reaching what? Finally reaching this row, which means this row only. Which means what? Your robot can only move in downward direction and will stop only when it has reached the last row. So these are the points that were given, and we have explained all the points, right? We have understood all the points. Now अब हमें approach समझनी है. Let's first quickly look at this example and we'll see what is exactly required here. Remember, you have to return maximum number of cherries that can be collected, right? So this is robot 1, this is robot 2, and robot 1 moves this green path, and your robot 2 moves this blue path, right? So let's see how it is actually they're moving, right? let's say robot 1, let's say, let's keep a count of cherries collected by both the robots. Robot 1 collects this cherry because robot 1 starts from this point, at as it was already given in the question, right? That robot 1 would start from the leftmost corner, uppermost corner, and robot 2 would start right uppermost corner, right? So these are the default positions of robot 1 and robot 2, and they have to collect these cherries, right? They don't have any choice, they have to collect these cherries. So robot 1 would collect this 3 cherries on that block, and they have to collect all the cherries on that particular block, and robot 2 would collect one, right? One cherry, right? Then robot 1 would move downward and would collect two cherries, and robot 2 remember I am only explaining the path they are following. Robot 1 here has two choices, right? It cannot move here, it cannot move lower diagonal leftward, right? Because it will move out of the grid, and that's, we cannot make any movement out of the grid. So robot 1 has only two choices, this and this. Unlike and robot 2 has this, these two choices, right? These two choices. Robot 2 cannot also move there because it would move out of the grid then, right? So let's say robot 1 collected this 3, then robot 1 moved downwards and collected this 2 also, simultaneously. Robot 2 also moves, robot 2 won't wait for robot 1 na. Robot 2 won't wait for robot 1, and it has to move simultaneously with robot 1, which means robot 2 moves somewhat here or here, collecting this cherry, which means robot 2 would collect all these 5 cherries. Then robot 1 would move here, and robot robot 2 is moving here. But what are the possible directions it can go in? Robot 1 was here and has collected all the 2 cherries, right? And has collected all the 2 cherries, and robot 1 has again two choices. It was supposed to be 3, but it cannot take this choice. At by taking this choice, robot 1 would move out of the grid, right? So robot 1 has two choices. What choice robot 1 would make would be to consider the max of these two choices, right? To consider the max of these two choices. Similarly, let's from the beginning, robot 1 collected this. Robot 1 can move here, robot 1 could have moved here, but robot 1 collected this and robot 2 collected this. So somehow they made maximum cherries in robot 2. Let's say robot 1 moved here, and robot 2 had only one choice, right? Robot 2 had only one choice. If robot 1 has already reached here, robot robot 2 would not go here, because he won't be able to collect the same number of cherries again, because both of them would be on the same cell. Both of them would be on the same cell, and for the same cell only one of them could collect the cherries, right? So total sum would be, let's say total sum would be, if they made this move, like robot 1 moved here and robot 2 also moved here, the total cherries would be 3 plus 1 plus 5, which is 9. But if robot 1 moved here and robot 2 moved here, which means the total number of cherries would increase to 3 plus 1 plus 5 and plus 1 again, this one, right? This one plus 1 again, which would be 5 plus 6 9 and 10. This would be the other case. But the actual movement made by these two robots was, robot 1 moved here, robot 2 moved here, collecting the maximum cherries in this step. And what are the number of cherries? Let's count. 3, 1, 2 and 5 by robot 2, right? So 3 plus 1 4 plus 2 6 plus 5 11. So in just one move made by both the robots, they collected maximum cherries that can be collected in that move. So we have to take maximum at every moment, right? Maximum at every moment, so as to maximize the total number of cherries collected along the way, right? You have to understand this, right? So this is how the movements are being made, right? This is how the movements are being made. Robot 1 moved here, robot 2 moved here, collecting the maximum cherries. Now again, robot 1 has two choices and robot 2 has two choices. Now robot 1 moved here and robot 2 moved here, right? Collecting the making the total cherries again maximum. Total cherries, let's say sum again maximum on this row. It was already maximum for this row. Again they made a move simultaneously and they made maximum cherries on this row also. Then what happened? Robot 1 moved here and robot 2 moved here, again making the maximum at the last row. So they are making the moves such as to maximize collected cherries, total number of collected cherries at every step they have taken, right? For example, they moved here, both of them made their first move simultaneously, and in their first move only they maximize the cherries that can be collected in making one move. Then again, when they made second move, they again maximize the number of cherries that can be collected for the second move, right? So what are they doing? What are they doing? They are maximizing the cherries at every step, right? They are maximizing the cherries at every step. Now, how will we code it up? How will we code it up? Obviously, you know that when you have to consider all the possibilities, right? You could go here, you could go here, you could go here, you could go here. Again, you have choices. Again, you have three choices for here and two choices for here, and again three choices, two choices, and last row. So when you have multiple possibilities and you have to find particular case out of those, what is the particular case of this question? The particular case is you have to collect maximum number of cherries at every step so as to maximize total number of collected cherries. What you'll do? Maximize cherries at every step. What this will do is this will automatically maximize total cherries, right? Total cherries. So this would be our approach. So and if you already know that when you have to consider all the possibilities, what you do? You follow recursion. Then what you do? First of all, for possibilities, let's say for possibilities, you go for recursion, right? Then you minimize the time complexity of recursion using BP or memoization, right? Memoization, right? So this would be our approach. And we have to write the recursion, right? We have to write the recursion. So for writing recursion, you have to first understand that the movements are being made how. Let's say I have already explained the movements are downward, rightward diagonal, leftward diagonal, downwards, right? What are the movements, right? We have already taken the movements. That would be, let's take it again. Movement would be, let's say I and j was the original index. So one time you are increasing and decreasing, right? One time you are increasing I and decreasing j again, right? This is the one movement. In second movement, you're increasing I and keeping the j same. You're increasing I and keeping the j same. And in third moment, you're increasing I and j both, right? So plus one for I and j both. So these are three possible movements, right? These are the possible movements, right? But what if I say that your I is already always increasing in every moment? Now look at this carefully. Your I is increasing automatically, like by default, it is increasing in every moment, every of the three movement. So we can say that I is automatically increasing. I would increase every time, right? Every time a move is being made, I would increase, right? What would be the differentiating factor of the movement? The differentiating factor would be the column in which the column is changing. How? Column is decreasing one when I is increasing, column is keeping same, column is being same when I is increasing, and column is increasing when I is increasing all the three cases. So what are the movements? J is moving. J represent what? Column. So column is changing like this, these three, and I is always changing like what? Always increasing by one, right? So this is the movement, right? Let's understand how will we write the recursion. What we'll take as you know that both of the robots are moving simultaneously, so row would be the same for both the robots. For example, they're at starting position, they're already in the same row. When they make one move, then both the robots would come here in the second row, and when they make third move, both the robots would come in third row, right? So row is same for both the robots. So I can say I don't have to keep a track of row separately for both the robots. I would just have to take our common symbol that would keep the track of rows of both the robots. But column is changing differently. Like for example, here column is decreasing by one, and here column is keeping the same. So column is changing differently. So I would say that column for first robot and column for second robot, I have to take separate symbol. I have to take separate variables to keep a track of, right? To keep a track of both the columns, how they are changing, because they are changing differently, right? This is the function definition. This is the major important things which I'll be passing. And what I'll be doing, let's write the recursion. For every step, I have to count the cherries. Let's say cherries at the current position. First I have to count now. So let's say cherries I have initialized with 0, and I have to count the cherries at that position. How would I count the cherries at that position? Let's say this matrix was grid. I would say just do one thing. Consider cherry plus the cherries present at the position in which the robots are standing. And how would we get the position in which the robots are standing? By what? Row and column 1 for robot 1, row and column 2 for robot 2, right. So what we'll do, I'll say grid. Just add the cherries of robot 1 in which column, in which cell the robot 1 is standing, and also add cherries for robot 2 in which the robot 2 is standing, the robot 2 is standing, right. Correct. Then what I'll do then what I'll do then what I'll do I'll say I have to take the maximum, right. I have to take the maximum, and I have to make a move, right. I have to further call this function for next possible movements. And what are the possible movements? 3 for every cell, right. 3 for both the robots, right. 3 possible movements for both the robots. So I'll say just do one thing. Just iterate a loop for I -1 to I plus 1, and inside that again iterate a loop for j -1 to j plus 1, and calculate what? Calculate new column 1 and new column 2, because you have to consider all the possibilities. That's why I have taken an n square loop, like loop inside a loop. Why? Both the robots are not moving in the same direction, right. Both the robots are not moving in the same direction. For example, what I mean by same direction is, if this robot makes this move, so this robot must make this move. If this robot is going downwards, then this robot also should go downwards, if they're supposed to make same moves, right. But they're not making same moves, right. So what we'll do is we'll just how they're moving. They're moving randomly on all possible directions. So there would be 6 possible cases, right. 6 possible cases. What would be the 6 possible case? Let's say this robot goes this. Keeping this constant, this robot can move this, which means for this movement we have 3 possible movements for robot 2. Similarly, if this robot 1 doesn't move like this and goes like this, then also we have 3 possible movements for robot 2, which are these, right. And if the robot 1 goes like this, again we have 3 possible movements for robot 2, which are not dependent on the movement of robot 1, right. Which are not dependent on the movement of the robot 1, which means there are 6 possible movements which would be made by robot 1 and robot 2, right. By robot 1 and robot 2. That's why we have taken an n square root. And how would we calculate new column 1 and new column 2? By just adding I on this and adding j on this. That's why it will consider all the possible movement, all the possible 6 movements that I have already explained right now, right. So this is the loop for calculating new row, new column, right. Why are we not calculating new row? Because in every movement the row would be increased, so we don't have to calculate new row separately. What we'll do is we will take a maximum, let's say maxi int minimum outside this, and we'll say just do one thing. You have to make the movements, right. Robots have to make the movements. And how will they move? Just take the max of what? Take the max of maxi, current value of maxi, and what? And the cherries you have collected on that particular step in which you are already on, right. And further calling the function for what? New row, which is row for +1, because row is increasing every time. And for new column 1 and new column 2, right. New column 2. That's what you will do. And what this will return in maxi would be the maximum what? Current cherries plus next max cherries. Current cherries, if just understand, current cherries is 3 plus 2 5, right. 3 plus 2 5. Then what? Current cherries is 3 plus 5 8. So I would return 8 rather than returning 5. But in this case, but as robot 2 is also moving, so I would consider both of the robots and return max of both So 3 plus 2, 1 plus 5 would be the max case. Max case would return me cherries. How much? 3 plus 2, 5, and 1 plus 5, 6, which means total of 11 cherries, which would be the maximum, I can attain by making just single move, right? So that this is why we have taken maximum of current cherries plus further calling function for all the possible six position. What are the possible six position? This, right? So we have to consider this case. We have to consider this, right? This is the actual code, how it's working, right? This is the actual code. Now let's understand what is missing here. We have considered six possible movements, right? These six possible movements, but what we haven't considered is a very crucial case which is mentioned in the points. When both robots stay in same cell, only one of them takes cherry. But according to this logic of ours, we are just adding the cherries. Just adding the cherries of both the robots cell. Let's say both the robots came here, but according to our logic, this five series would be counted twice, because we haven't put any condition for both if both of them are on the same cell. So what we have to do, we have to add a little condition. If what will say, if your column 1 for both, if both the robots are in the same column, right, they would be automatically in the same row. I have taken that in account by increasing it only once for both the robots and keeping the row same for both the robots. So row would be the same. Just clear it out. Row would be the same. What you have to check, whether the column is same. If the column becomes same, that I can say, as the row is already same and the column also becomes same, I can say the both the robots are on same cell. And for same cell, I just have to take the values of that current cell only once, either column 1 or column 2. Both of them would return same thing, na? So this case I have to add, right? And what we have to do, we have to see base cases, right? Base case would be very easy, right? Very easy. If this moves out of the bound, if this any of the robot moves out of the bound, which means we have to return 0. That this is not possible way, and no cherries would be collected. Return 0, right? Then or else what can be the base case? What can be the base case? So this is the base case. Like, this is the enough base case, because eventually if we apply out of the bound, if we don't apply a base case for last column, reaching the last column, stop, right? This is the base case, huh? This is the case given that both the robots should reach the last row. If we do not add it separately, it would be covered in out of the bound logic. How? Because this robots are making only 3 movements, which is all 3 of them is downwards. So eventually these robots would come simultaneously in the last row, and on making further movement, the out of the bound base case would be triggered. So eventually, without adding a separate base case for the last row, they would reach last row without adding actual separate logic. So we'll just have to add out of bound logic. And you also already know out of bound logic, right? Out of bound logic, if row is greater than, if row is less than 0, or equal to rows ka size, grid ka size, right? सिमिलर फॉर कॉलम ऑल्सो, कॉलम लेस देन 0 हो जाता है, या फिर कॉलम साइज के बराबर हो जाता है, राइट? सो दिस इज आउट ऑफ बाउंड केस, बेसिक आउट ऑफ बाउंड केस, राइट? सो लेट्स फर्स्ट क्विकली गो थ्रू द कोड, देन विल सी द टाइम कॉम्प्लेक्सिटी, राइट? सो लेट्स क्विकली गो थ्रू द कोड. So let's quickly understand the code. In the code, this function was already given. I have just taken rows and column size, and I have just ignore this. I have taken what answer variable and passed the values in the function. In the function, I have made separately. And what is the definition? I have just taken a common row for both the robots variable, and column 1 and column 2 for separately for both the robots, and I have passed the grid, right? And I have considered n and m, which is the grid size. For considering base case would be if row less than 0, or any of the column becomes less than 0, that would mean out of the bound, return 0. If row becomes equal to the total number of rows, or either of the column becomes equal to the total number of columns, right, then I would say return 0, because base case is triggered. It wouldn't move out of the bound, right? Wouldn't move out of the bound. This is the out of bound oob case, right? Oob case. And just as we discussed in the logic, I have just taken items, or you can take also take cherries of that current cell. what I have done, if the column is same, just consider one of the robots series. Just consider the series one time only if both the columns are same, which means that both the robots are on the same cell, right? Both the robots are on same cell. Then consider that cherry, that ground cherry only once. So this means that, right? And if else case would be both the robots are on different cells, then consider both of them, obviously, right? And for taking maximum out of the all possible cases, we have to take maximum at every step. And how will be the movement way? I have already explained in the discussing the logic. So right, so I have declared max c 0, and I have made the movement from I minus 1 0 1 and j also minus 1 0 1. This would consider all the possible gates: minus 1 for minus 1 0 1, 0 for minus 1 0 1, and 1 for minus 1 0 1. So all possible 6 movements made by the robots would be considered, right? I have calculated new column in 1 and new column 2, and I have just taken max of maxi and items. What is items? Current series on that particular cell. How many series are there on that particular cell? And further call the function for row plus one and new columns, right? So this is our code, and at the end I've just written maximum. Obviously we have to written maximum, right? So I have just written maxi. So this is our recursive code. Let's quickly go through the time complexity of this code, and we'll also see how will we optimize it, right? Now let's quickly go through the time complexity of this approach, this recursion approach, which would be obviously very huge. Let's see how many recursion calls are being made in a particular function calls, right? In a particular function call would be increasing the value of these, right? So I can say for a particular robot, I am making three function calls, right? I am making three function calls in all three directions, or in all three downward directions. So I can say three function calls are being made. And how many further function call in a particular function call can be made? So understand this. How many further function call would be made until we have explored all the rows and all the columns, which means until we have gone through all the rows and all the columns, right? So this would be our time complexity, 3 to the power rows into columns, which is very giant. Further, if we optimize the recursion code, which is giving us giant time complexity, we'll be optimizing using DP, right? Which would be memoization, either memoization or tabulation. You can go by either of the methods, right? So let's understand how would we actually make a DP table in this. So to make a DP table, I've already explained in my previous DP videos. Just look at in the function, in the recursive, which is recursively calling itself, and see how many variables are getting changed in one function call. So you can say that in one function call, three variables are getting changed, right? New column 1, new column 2 is getting calculated here, and row is increased by 1 in every function call, right? In every function call. So I can say that in a particular function call, three of the variables are getting changed. And if three of the variables are getting changed, so I can say the DP I have to make would be of three dimensions, one for row, one for row, one for column 1, and one for column 2, right? Three variables, right? And I can say that I just have to initialize it with -1, -1, right? And I'll pass it. DP memorization very easy. Just pass the DP. I have already received the DP here. What I'll do is I'll just before making any of the function calls, I'll just say, hey DP, whether you have already calculated the value or not. I'll just see, hey DP, have you calculated the value already for these three variables? If you have calculated the value, then you must not be having -1 at your place, because I have initialized you with -1, and if you have already calculated the value for these three variables, then you won't be having -1. And if that's the case, just return whatever the value you have. Don't make any unnecessary function calls for that row, column 1, column 2, right? Just return whatever you have, right? And if that's not the case, and your value is -1, that means you haven't calculated for these three variables. So make function calls, and store the answer in that variable, in that space, right? So this is our DP approach. DP is very basic, very easy. Memorization is very easy, right? So let's quickly go through the time complexity of this approach. See what will happen in DP, you won't be making any unnecessary calls, right? You won't be making unnecessary calls. What you can do in worst case, you can say that this robot will cover all the columns, right? This obviously both the robots would be going simultaneously row wise, right? Row wise. Yes, and what can happen in worst case? In worst case, both of the robots would travel to all the columns, right? These three columns for both the robots. This robot also goes through these three columns. This robot goes through these three columns at least once. In worst case, right? So I can say if both the robots are going increasing are moving downwards, so row would be always be changed only once. But in worst case, both the robots can iterate the column once. In worst case, so for robot 1 is iterating the column once in worst case, and robot 2 is also iterating the column once in worst case. So I can say that the time complexity would be row into column, right? Row into column, and space complexity also would be 3 dimension, which would be see rows, which is the rows size, into column size, so that would be my space complexity. Rows into columns, that would be my space complexity, and this is my time complexity. So this is the basic approach. And see how much it is getting reduced in memorization. 3 to the power rows into columns, 2 rows into column. See how much it is reduced. So this was all for today, and this is our memorization approach. This is our regression approach. If you haven't understood any bit of this question, just drop down a comment. I'll reply as soon as possible. And do try it using tabulation. I don't do tabulation in my videos because it would make the video very long. And if you know tabulation, just try it with tabulation for the minimizing time complexity and space complexity also. It won't necessarily reduce time complexity, but it can reduce in some cases space complexity. So do try it, and I'll just paste that link of the problem in the description. Do try it, and code करती रहिए, code मत छोड़िए. All the very best.